Hey, welcome back, everyone. We have Melody Chan to open the morning on Hopf Algebras and the Cohomology on stage.
Thank you very much, June, and to the organizers of this conference for bringing us together in this exciting configuration. So the work I will sort of go towards is work that is joint with Francis Brown, Soren Galatius, and Sam Payne. Sam is around here. Sam's right there. You can find it in the archive. And but I will try to give a sort of introduction to the circle of ideas that I've been considering for some time, actually since graduate school in some sense. So please stop me with any questions or comments. That would be great. So, okay, here are some things that I pretty much will only talk about in small portions or not at all. There are various, the paper I want to talk about had many different aspects. And if the four co-authors were to give talks, we would likely give largely disjoint talks. There are a lot of different aspects. So this paper involves tropical moduli spaces of curves and abelian varieties. But it also has something to say about fundamental constructions in algebraic K-theory, and indeed these shall be related to tropical moduli spaces. And then also in the background, and possibly of interest to the physics-oriented portions of this audience, is a whole story about invariant differential forms on symmetric spaces like the positive definite cone. These will be sort of secretly the source of some cohomology classes in the tropical moduli spaces. And then the sort of main characters in my mind, though they are not necessarily a focus of this audience, which is perfectly fine, the main characters are certain fundamental moduli spaces in complex algebraic geometry. The moduli spaces MG of Riemann surfaces or algebraic curves, and the moduli space AG of abelian varieties. So I will touch on some, but not all of these different concepts. And it's a long paper. There are lots of different aspects, but I'd like to give you one take on it. So let me start with one of several possible introductions. All right, so it seems that the stated meeting point in this meeting is combinatorics. We all love combinatorics. And an angle that one could take is that it actually can have something quite interesting to say in the study of algebraic geometry, which, let me recall for you, is the study of zero sets and perhaps non-zero sets of polynomial equations. Such sets are called varieties, and I'll be interested in complex varieties, so solutions and non-solutions to polynomials with complex coefficients. And in particular, it's very interesting classically interesting to study the topology of such complex varieties. It's much more specialized than studying sort of arbitrary topological spaces. And I claim, and this will be sort of my introductory section, which is probably the most important section of this talk, I claim that combinatorics has something to say about the topology of complex varieties. So I guess this is our meeting point. This is where my motivation is coming from. And yeah, if you don't mind me suggesting a moral of the story, which you're welcome to ignore, one possible moral is that combinatorics can say even more if you put a little geometry back into the story. This might be, so geometry related to combinatorics, perhaps that of simplicial complexes, polyhedral complexes, or fans, and in particular, something called tropical geometry. I'll give you a slogan for tropical geometry, and then I'll give you a cartoon example to start out. My slogan is that tropical geometry is a degeneration technique in algebraic geometry, in which the limiting object, rather than being a variety in any way, is entirely combinatorial, e.g. polyhedral. This is one take on tropical geometry. Certainly it has many different aspects that some others in the audience are more familiar with than I am, surely. The idea of degenerations in algebraic geometry is itself quite ancient by my standards. But this is a sort of modern take on it in which one passes sort of entirely to a combinatorial limit. So now let me give a cartoon example. So here's my cartoon example. It involves the variety C star squared, so pairs of non-zero complex numbers. The algebraic torus of dimension 2 over the complex numbers. Here it is drawn in, what color is that? Pink. And one can profit by compactifying it, that is to say, putting it inside a compact variety, in this case, the projective plane, such that the stuff that you add is what's called normal crossings. So this is an example of normal crossings. This is a normal crossings divisor. It's come up before in this conference, like in Chris's talk, for instance. This is a situation where you have codimension 1 subvarieties, in this case, the line x equals 0, the line y equals 0, and the line at infinity, such that locally they intersect transversely. They're locally modeled by the intersection of coordinate hyperplanes inside an affine space. So this is a variety. It's sort of a cartoon example. I'm not expecting you to get extremely excited about insights about the topology of C star squared. But there is nice combinatorics already when considering the variety C star squared inside its compactification P2. Here is a poset of boundary strata. Notice the inclusion reversing nature of this poset. The divisors, dx, dy, and the line at infinity, d infinity, are at like level 1, I guess, of this poset. Below, you have the 0-fold intersection of the divisors. Here you have the 1-fold intersections. And here you have the double intersections, which are exactly the 3 points, each point contained in 2 divisors. Is this poset picture clear? So in the world of combinatorics, one could certainly profit by just studying this poset. And again, a sort of moral that I'm somewhat artificially imposing on this talk is that one could profit even more to enhance this poset with just a little bit of geometry. So what I'd like to take is the so-called dual complex of the boundary. And then to be more precise, a sort of infinite cone spanned by that dual complex. This cone, it's abstract, so it's sort of obtained by gluing polyhedral cones together along faces. And it has 1 ray for each of the 3 divisors. It has 1 2-dimensional cone spanned by any 2 divisors if they intersect non-trivially, and so on and so forth. And so for me, this will be, let's declare it to be the tropicalization of this torus inside P2. So it can be remembered merely by this poset, but there's a little bit more geometry available to us. Is the cartoon example okay so far? So back to my sort of moral, if you will. The combinatorics could say even more for you about topology of complex varieties if it's infused with geometry. For example, I think we've seen already over the last few days of this conference that there are certain definitions that one could make, especially if one is Kontsevich, like a very complicated definition. Well, it's not complicated. It's a combinatorial definition that we saw on Monday of a certain graph complex spanned by graphs whose differential is a sum of one-edge contractions. And it's already been noted that it's a little tricky to get the signs right, to get d squared equals 0. And this was noted, also a similar story was noted, I think, in a talk yesterday morning. But if you can promote this kind of graph complex, for instance, to space, to have a space level instantiation such that the differential actually expresses something that comes from topology, an actual differential in the usual sense of algebraic topology, then this sort of explains after the fact, or maybe more conceptually and maybe in a way that could be useful to you, certain sort of constructions that can a priori be articulated purely combinatorially. And similarly for the so-called Kohn-Kreimer coproduct and graph, which we will see perhaps, if I have time, enter this talk a little bit later. So one would like to see it as a sort of after the fact construction that comes from a space level coproduct on a certain space. And my second reason for this slogan is that I'd like to put forth that once you have a bit of geometry associated to your combinatorics, one can work with tools on this level. For instance, some kind of de Rham theory on the level of tropical geometry. And in our situation, we actually did use results of primarily of Francis Brown and Oliver Schnetz that involved integration of very, very particularly chosen differential forms directly on certain polyhedral, in other words, tropical spaces. And these integrals are interesting examples of, it's like small examples of Feynman integrals, and they're sort of an engine in the background in our work, even though this won't be the focus of my talk. Any questions or comments? All right, so let me say things a little bit more precisely, keeping in mind our cartoon example, but looking forward to more interesting examples of varieties with things like MG and AG replacing the two-dimensional torus in our cartoon. So let me recall the notion of compactly supported cohomology, since this will just be convenient for me to phrase our results. So for any reasonable space, such as any quasi-projective variety, simplicial or polyhedral complex, etc., recall or take this as the definition that the compactly supported cohomology is basically just the singular cohomology, the usual cohomology of the one-point compactification of that space. It's the cohomology of the one-point compactification taken relative to the point at infinity. And if you don't want to have that clutter in your mind, you can forget about that and you'll be right for all positive k, basically. Recall that this singular cohomology group is with q coefficients. It's a rational vector space, roughly speaking, which detects k-dimensional holes in your space. So it's a rough measure of the topology in degree k of your space. And I'll, for convenience, phrase the results that come in the next slides in terms of compactly supported cohomology. Recall that in the situation of a manifold X, or in this case, even an orbifold, you're not really losing any data. No data is lost passing between singular cohomology and compactly supported cohomology, e.g. because of Poincare duality. All right, so with that out of the way, one of many interesting consequences of Deligne's work on mixed Hodge structures more than 50 years ago can be phrased as the following theorem. And I recommend, if this is new, keeping in mind the cartoon example. So the theorem is that if you have a smooth compactification, X inside X bar, of your complex variety X, whose boundary, meaning the stuff you added, is normal crossings, meaning looks like the transverse intersection of coordinate hyperplanes, then I claim that there is a canonical injection from the compactly supported cohomology of the tropical variety associated to your pair into the compactly supported cohomology of your original complex variety with its complex analytic topology. So again, here, this refers to the so-called tropicalization of this pair, and it occupied the middle third of my cartoon example in the previous slides. There's evidently a lot more to say about this, which I'm only saying a little bit. Particularly, I'm saying the part that is most combinatorial in order to sort of adjust properly to this audience. This image of this injection is a canonical part. It's a canonical subspace of this compactly supported cohomology group called the weight zero subspace and denoted W sub 0. If this happens to be new, then you can take this as the definition of the weight zero subspace. Although I suppose, to be fair, I haven't told you what the injection is. But you can take this to be the definition, or let me tell you or recall for you that this is like the smallest subspace in a particular filtration defined by Deligne on the compactly supported cohomology of, in fact, an arbitrary complex variety, smooth or not, compact or not. This is sort of half of the data of a so-called mixed Hodge structure on these cohomology groups or compactly supported cohomology groups of a variety. This data is a certain filtration called the weight filtration, and this is the smallest subspace in that filtration. And in some sense, it's combinatorially controlled. And that's where we're zeroing in to get some results on cohomology of complex varieties by studying cohomology of their tropicalizations. So let's carry through our cartoon example just a little bit until we can't milk it for anything more. So, consider this tropicalization of the two-dimensional torus inside P2. It looks like a three-dimensional ice cream cone. And in order to visualize, the compactly supported cohomology, let's actually take the one-point compactification, which now looks like a football. And you can see that it actually has a, I guess, two-dimensional hole, which is the sphere itself. And, oh no, definitely tonight. Is that me? I can't see this. Okay, maybe this will just go away on its own. I can't see. Okay. Let's try our chances here. All right. Yeah, okay. So the fact that there's non-trivial cohomology in degree 2 implies, if you accept the previous slide, that we've found an interesting class in the, I guess, compactly supported cohomology of the torus, and it lies in a particular weight zero subspace. So this theorem I phrased as a theorem relating the sort of second level, the tropical level, and the top level, the algebrogeometric level. I could have phrased this statement at the pure combinatorics level involving just this poset. And yeah, one can certainly do this. But for the reasons I mentioned, I currently prefer the intermediate level of tropical geometry. For example, so that if one is very careful, one can profit from interesting forms. Thank you. So that one can profit from interesting differential forms that could be defined, for example, on these simplices for appropriately chosen varieties, in our case, moduli spaces. Yes?
Can you say a bit more about what you mean by canonical here?
Like this inclusion?
Yeah, why did you say it's canonical?
Yeah, yes. So I'm black boxing a huge theory, which I'm sure you have some familiarity with, but let me just sort of say for the room that, if you have a topological space, it has some cohomology groups or compactly supported cohomology groups. But if that space has the structure of a complex variety, which is a very special thing, then there's some additional structure one can put on the cohomology, respectively compactly supported cohomology groups, as shown in seminal work of Deligne about 50 or more years ago. And so part of that structure includes something called a weight filtration, and the other part is like a Hodge filtration that equips each associated graded of the weight filtration with an appropriate Hodge structure. So it generalizes like Hodge theory for the case of smooth projective varieties. And there's a lot more to be said here, but I'm claiming that this one subspace of the weight filtration is combinatorially controlled and exactly in this manner. Did I answer your question? Great. Any other comments or questions? Yeah.
So I want to define differential forms on the tropical and then pass to the classical. Can I do this for any variety?
Yeah.
My favorite variety and its tropicalization. Am I ready to get?
Please do. Yes. Yes. In my opinion, you are, but I At the moment, I'm at a sort of very delicate part of my own development in the subject where we have these rather amazing differential forms that were provided to us through the work of Cartan and others as elucidated by the work of Brown. And those forms, whose integrals over appropriate simplices and tropical moduli spaces are examples of Feynman integrals, are exactly what we needed to sort of behind the scenes in this work. Yes, but I think this would be very, very interesting. And in particular, there's a sort of perspective that I'm learning from my collaborators in which these simplices themselves is a little bit like the discussions on positive geometries, where these simplices, I mean, they look like just real triangles or something, but one should view them inside, you know, as a chamber of, a connected component of the complement of some variety, the real points thereof. So, I mean, on some level, there's some algebraic structure to be restored here. But yeah, for the moment, I think that this story in principle works. It's just a matter of finding the right forms. Any other comments or questions? Yes.
Consider instead of the one-point compactification, so projective compactification, meaning that you have this point of code,
Yeah.
just intersect it with the student, say.
Yes, this will be the same thing with a degree shift. So the statement is that if you have a space and you have its suspension, then the two, you know, the cohomology of one is the same as the cohomology of the other up to a shift in degree 1. Yes, so I've decided to, for various reasons, I'm phrasing it this way. Thank you. Yeah, so if you wanted, you could talk instead about the cohomology of like the dual complex itself, which in this picture is like the open triangle with degree shift 1. Thank you. Other questions? Okay. All right, so enough cartoon. The actual spaces I'll be interested in are very classical moduli spaces. In this talk, supposedly, I'm driving towards the study of AG, the moduli of abelian varieties. But MG will play an important role as well, the moduli of Riemann surfaces. Okay, sorry for all the experts, which is probably most of you here. Let me give you my quick definition of a moduli space, since I didn't know this as a graduate student. So a first definition is that it is a parameter space for isomorphism classes of geometric objects of interest. And here's my cartoon example. Again, major apologies to the experts. A moduli space for squares in the usual sense of like elementary school geometry is given by this open ray. It's a coarse moduli space, so it doesn't have all the properties we might want in the sense that families of squares correspond to sort of walks around this moduli space. But it does have the property that every point corresponds to a different isomorphism class of squares, and these are arranged in some way such that the topology on this space communicates our desired notion of nearness of two squares. Okay. This is also a cartoon example. I promised to talk about, in fact, some new structures that we discovered in our work in the cohomology of the moduli space AG. Actually, really the moduli space of all AGs all at once. And that new structure that is, I think, interesting and new is the structure of a Hopf algebra. But we'll get there. For now, let me tell you or remind you that AG denotes the moduli space of abelian varieties, principally polarized abelian varieties of dimension G. And it's a complex variety, or really complex orbifold of dimension G plus 1 choose 2, if I remember that right. And let me mention for the group theoretically inclined that like all the moduli spaces that are appearing, I guess all 2 of them in this talk, are also classifying spaces for groups. In this case, pi1 is the symplectic group, SP2GZ, the group of invertible matrices of size 2G by 2G that preserve a particular fixed alternating form. So like this story that I'm telling is a story about cohomology of moduli spaces like AG, but definitionally, it's also a story about cohomology of groups like sp2gz and other arithmetic groups. So, you know, how does one study groups in the modern world? By spaces they act on. There is a purely algebraic way to define the cohomology of a group, but here it's fine to take this if the right-hand side happens to be new. It's fine to take it as the definition. It's the cohomology of whatever this space is. But let me start with the moduli space MG, the moduli space of Riemann surfaces or algebraic curves of genus G. It's also a class, oh, so this is a ridiculous cartoon, also completely inaccurate, of MG. The point is it's a parameter space for all possible complex structures on a fixed topological surface of genus G. And this is also a classifying space, namely for its essentially fundamental group, which is famously the mapping class group mod sub G. Okay, so here's, oh yeah, sorry, I think my whole talk is cartoons. I mean, these are totally inaccurate pictures. This is an inaccurate picture of an important compactification of MG, denoted MG bar. This is a cartoon of the Deligne-Mumford compactification by so-called stable curves. So stable curve is like a nodal Riemann surface, which furthermore has finitely many automorphisms. This is a picture right here. You can imagine it as a degeneration of something on my previous slide. You imagine walking to the boundary and one of the geodesics here interpreted with the hyperbolic metric is getting shorter and shorter, like this waistline. And then in the limit, if you do the right thing, thanks to the work of Deligne-Mumford and many others, you can add, you know, a boundary divisor that parametrizes so-called stable curves in which one now can admit nodes among the singularities. Sorry, the only singularities, if any, are nodes. This is a variety of dimension 3G minus 3. Oh, and I should mention that there's a corresponding story with marked points, thanks to the work of Knudsen. And I won't visibly talk about this, but I should have, because this will exactly correspond to the case of external legs or marked points on the associated combinatorial objects, which will be graphs. So sorry about that, but there exists such a story. Then there's a tropical moduli space denoted MG trop. This is a moduli space of tropical curves. Oh, you know what? Sorry, let me go to level 3 first. So roughly speaking, the Po set, okay, yeah, let me suppress some details to get the main point across, hopefully. There's a stratification of the boundary, namely the stuff you added, and the strata are controlled by, roughly speaking, a Po set. And the Po set is, the elements of the Po set are stable graphs, so-called. So I drew an example for G equals 2 and a very rough idea of how you might get a stable graph or what its definition is. So in this example, which is a cartoon of a stable curve of genus 2, you can see that it already has some non-trivial combinatorics. It has 2 irreducible components. They meet at a node, and they each have geometric genus 1. And that's the data of a stable graph, thus extracted. Okay, so the middle level of my narrative is the moduli space denoted MG trop. This is a polyhedral space, roughly a polyhedral cone complex, more officially something called a generalized cone complex. And it parametrizes metric stable graphs. So pictures like this together with a metric on the edges. And hopefully this makes at least intuitive sense. You have some like cones. Each cone is labeled by one of these pictures, but the individual like actual points in the cone can be regarded as a like choice of a particular stable graph together with some actual lengths on the edges. So some numbers associated to the edges, which we view as lengths. In this way, MG trop is, roughly speaking, a space. Actually, no, this is actually true. MG trop is a moduli space. Its points are in bijection with isomorphism classes of metric stable graphs. And it has an ancestor from the 1980s in Color-Voigtman outer space. And the connections are interesting, and I can't quite, this is not the main point of my story, but the idea of taking spaces of metric graphs to study cohomology of arithmetic groups or arithmetic group-like groups is old and goes back to this amazing work of Mark Color and Karen Voigtman, and a lot of work since on so-called moduli spaces of metric graphs in outer space. Here, okay, sorry, let me not get too much into that. The fact that this is the right picture was provided, it was a theorem due to Abramovich-Caparaso-Payne. So I hope it's clear what the content of this theorem that I'm claiming is, that in a precise sense of taking tropicalization, a particular sort of synthetic definition of MG trop as a space of metric stable graphs really is the tropicalization of the pair MG inside MG bar. Any questions or comments? So then in the bottom right, I've reminded you, I guess, because it was discussed a bit on Monday, of an older theorem together with Soren Glatius and Sam Payne that says that, let me phrase it this way, that the total weight zero compactly supported cohomology of MG, this is for like all genera at once, and is thus a bi-graded vector space, graded by degree and genus, can be identified with the cohomology, with degree shift, which is unimportant, of Koncevich's commutative graph complex, which annoyingly I've denoted differently than Mishi. I've denoted it GC2. So again, this is sort of like the starring, it plays a starring role on the MG side of this story. Perhaps it looks technical, but remember that it's exactly, by this comparison theorem I was discussing, exactly the totality of the data of the compactly supported cohomology of these polyhedral spaces, MG trops. Yeah. Yeah. Yeah.
This picture that you're showing
Yeah.
of these two triangles touching each other.
Yeah.
Do you think of it as a combinatorial picture, meaning that there are some abstract syntheses that are abstractly joined together, or is that an actual fun in some geometric space?
Thank you for the question. It's definitely the former. So as like formally, I'll define it as like you take a bunch of polyhedral cones and you take a bunch of face maps, so inclusions of one cone isomorphically as a face of another, and you glue with like Elmer's glue. So you take the co-limit over an appropriate diagram of cones and face maps. So it, in particular, it doesn't necessarily sort of holistically embed in a like single vector space. That would be true for M0N trop, but not in general. And in particular, sorry, this is getting a bit probably too detailed, but face maps include automorphisms of cones. This can happen. So this roughly is sort of hiding a slightly more interesting data structure called a generalized cone complex. Thank you. Other comments or questions? Okay, so let me, okay, I'm gonna take this box and zoom in on the next slide. Yeah, so GC2 here denotes Koncevich's commutative graph complex developed in his paper of 1993. And sorry to say, it's just a slight convention difference away from what was introduced on Monday. So G sub G denotes the sort of homological graph complex as in Mishi's talk. So roughly speaking, generated by graphs with differential edge contraction. And here we take the totality of them over all G and take the graded dual. Okay, and then let me briefly mention, though this was mentioned on Monday, that this identification, like, you know, it had some surprising consequences. The work of Thomas Willwacher implied that a particular sort of slice of this bi-graded vector space can be identified with the Grothendieck-Teichmüller-Lie algebra, GRT. And this Lie algebra is sort of a central mystery. One thing to note is that it already contains, by work of Brown, a free Lie algebra generated by classes in odd degrees starting at 3. And this was already, you know, asymptotically grows quite fast, so provided sort of a new sort of surprisingly large, though dwarfed by the asymptotic Euler characteristic calculations from Monday, but it did provide a surprisingly large source of new cohomology classes in MG. Any comments or questions? Okay. And let me just remark that in particular, and I honestly don't know sort of how to think about this morally, but in particular, the thing on the left-hand side is a Lie algebra because the thing on the right-hand side is the homology of something, and that something is known to be a differential graded Lie algebra. And the Lie structure was discussed in Monday's talk. Okay, and now let me do the annoying moralizing thing, which you can ignore. I'm thinking of this statement as a geometric instantiation of the graph complex. Namely, it is the moduli space of tropical curves. E.g., it sort of looked non-trivial, maybe if you looked at Monday's talk just in isolation, that some complicated differential involving signs and orientations all works out so that d squared equals 0. But of course, if you have a topological space and an appropriate notion of, say, cellular homology, then d squared would be equal to 0. So that's my moral. Okay, the main player of today's talk is AG, which, okay, I'll give you a definition which makes it not at all obvious that this thing is a variety. I already did that for MG, so maybe you're not too unhappy. If I had defined MG, I could have defined it as the quotient of a contractible space, which is known as Teichmüller space by the action of the mapping class group. Here, the Teichmüller space is replaced by the so-called Siegel upper half space. This is definition, G by G symmetric complex matrices whose imaginary part, which is a symmetric real matrix, is required to be positive definite. The smallest example is one that maybe looks familiar to at least some of you. It is the example of G equals 1. Here, the Siegel upper half space is 1 by 1 symmetric complex matrices with positive imaginary part. That's the upper half plane. And this group acting is exactly SL2Z. So this is the picture. This is the only picture I can draw. So once again, by this description, and the fact that HG is visibly contractible, you obtain that AG is a rational classifying space for this group. There is a beautiful, intricate story about that roughly speaking, at least the way I'm telling the story, is an analog of the Deligne-Mumford compactification of MG. There isn't a favorite one in this world. It admits many interesting normal crossings compactifications. Slightly more generally, this is a theory of toroidal compactifications. See the work of Kempf, Knudsen, Mumford, Saint-Donat, and Ash, Mumford, Rappaport, Tai, for instance. And again, there's no favorite one, but for each choice of some combinatorial data called an admissible decomposition, one gets such a toroidal or normal crossings compactification. And in this way, although I can't draw it accurately at all, it, at least immediately, I could take some time, but it thus admits a tropicalization, AG trop, a moduli space of tropical abelian varieties. And this is very, very concrete, and I'll return to it at the end if I have time, and if not, if it's okay, I actually recommend a paper I wrote in graduate school, which is called The Combinatorics of the Tropical Torelli Map. And in particular, I wrote it before I knew that much, so it is very easy to read, in my opinion, because it's all about the combinatorics of this space, without all the business about mixed Hodge structures and stuff. All right, so this is the top level. This is the tropical intermediate level. And let me just mention that there's beautiful corresponding combinatorics, at least for an appropriate choice of toroidal compactification. There's some combinatorics that's controlled by a chain complex that remarkably relates to the notion of perfect quadratic forms from number theory. This is roughly the AG analog of the MG's graph complex, the one we saw on Monday. Okay, let me state some theorems. So one of our main theorems, this is in work with Francis Brown, Soren Glaetius, and Sam Payne, is that the totality of the weight zero compactly supported cohomology of AG. So this is a bigraded vector space. It depends on genus and cohomological degree with an appropriate shift. The theorem is that this admits the structure of a bigraded co-commutative Hopf algebra. Okay, now with apologies to the experts, I will give you my own crash course on Hopf algebras since I myself am not an expert. All right, so, and hopefully there's sort of sufficient interest in this kind of idea in this room. Roughly speaking, a Hopf algebra is a bialgebra. A bialgebra is something that is both an algebra, so it admits a multiplication map, and a coalgebra. It admits a co-multiplication map. So multiplication is a way of taking two things and smashing them together to get a third thing, and co-multiplication is a way of taking a thing and breaking it apart. Recall that in the tensor product, elements need not be pure tensors, so typically one will take a sort of sum over all possible ways in some reasonable sense of breaking a thing apart. A bialgebra is both in ways that satisfy compatibility that I can't get into, and a Hopf algebra for this talk you can think of roughly as a bialgebra. There are additional conditions, namely there's an additional structure of an antipode map, and there are lots and lots of compatibility conditions that I won't get into. These play a role, I know, in physics in various ways, and they play a really beautiful role in combinatorics. I'm not an expert, but I know there are such experts in the room. Okay, yeah, so to continue my crash course, since I myself am a non-expert, I am scared of Hopf algebras in full generality. However, like, yeah, okay, just to put that out there. However, Hopf algebras that are either commutative or dually co-commutative are, in a formal sense, no scarier than Lie algebras or co-Lie algebras, respectively. No, co-respectively. Sorry, co-respectively. And this is due to a structure theorem. So bear with me, this is part of my crash course. So the crash course is as follows. If you have an augmented algebra, meaning you've got an algebra and also a map down to your ground field, then let I be the kernel of the augmentation, and the indecomposables are then the co-kernel of the multiplication map on I. Think of this as like the non-trivial stuff that, like, modulo sort of the pieces, so to speak. And I claim these form a Lie coalgebra. Dually, the primitives of a unital coalgebra. So this is a situation where you have a coalgebra and you have like a map from K to your coalgebra. Let J be the co-kernel, and then the primitives are the kernel of the co-multiplication map. So yeah, I mean, both of these have the feel of, I mean, up to duals, they have the feel of things that cannot be broken up. And these primitives, as you can check as an exercise, form a Lie algebra. And the theorem of Milnor-Moore is that in the graded connected case, a co-commutative Hopf algebra is, I would say, recoverable from, it's like equivalent data to merely the data of its Lie algebra of primitive elements. The precise statement is that it's isomorphic to the so-called universal enveloping algebra of its Lie algebra of primitive elements. And recall, this is like a canonical way to turn a Lie algebra into an associative algebra. It's left adjoint to some appropriate forgetful map. Okay, so that's my precise claim about just how scared to be of Hopf algebras. Any questions or even better comments from the experts? So let me see if I happen to have this on the next slide. Oh, thanks for asking. In my view, that this sort of structure statement about finding the structure of a Hopf algebra on the total weight zero compact support cohomology of AG is like it's closely related to, this can be made somewhat more precise, but at the level of the slide, view it as an analog of the previous fact that the weight zero compact support cohomology of MG forms a Lie algebra. So I think these are sort of cousin statements. And very, very roughly speaking, if you have two abelian varieties, you can kind of glom them together by taking their product. Whereas in the case of MG, all your curves are required to be connected. There's sort of no like sum map. And so I think that sort of, again, very intuitively on a rough level, sort of explains the sort of difference between finding a literal Lie algebra structure here, and on this side, like the universal enveloping algebra of a Lie algebra. That's my rough opinion on that. Was that relevant to your comment? Okay. Any questions or comments? Okay, so I regret not pulling this out a little bit more explicitly for this audience, but let me mention that one can use integration of differential forms on the moduli space, the tropical moduli space AG trop, as carried out by Brown-Schnetz very recently. And using those results, we can show that a very large free Lie algebra generated in degrees 5, 9, 13, and so on, conjecturally going on forever, but based on computer calculations to date, up to 45, sits inside the Lie algebra of primitives of our Hopf algebra. And I should have said more about these. These are very much related to the so-called wheel classes. So in Mishi's talk, you saw these wheel graphs of length. The ones that are important to us have cycle length 5, 9, 13, and so forth. They are homology classes in Mishi's homological graph complex, and they pair with interesting cohomology classes in our cohomological graph complexes. And the associated integrals are of invariant differential forms. And if you are a K-theory person, you would recognize the 5, 9, 13, and so on as related to the K-theory of the group GL and Z, or GLZ. And this is not an accident. So this is all to say that we have this interesting source of fast growing, in fact, exponential growing cohomology. Since by Milner-Moore, we have a copy of the universal enveloping algebra of whatever this is inside our Hopf algebra. And universal enveloping algebras of free Lie algebras are famous to some people, known to be tensor algebras, and these grow fast. So I think my personal takeaway is that Hopf algebraic structures seem interesting on a conceptual level, but they also provide a source, a possible fast-growing source of cohomology because of these structure theorems. Namely, if you can find a bunch of stuff in the primitives, then you can, find a lot of stuff in your Hopf algebra using the Hopf algebraic structure. Yeah. Yeah. Eagle eyes. Yeah. It's like a de Rham theory, right? So these really are representatives of the real stable cohomology, like real stable de Rham cohomology of GL. And as such, I had to change this to R. Yeah, thank you. Other comments or questions? Okay, so extracting from the previous result, and there's more to the story that I'm not able to say here. Sorry, not because it's a secret, I just don't have time. We can deduce that on certain sort of diagonals inside our bigraded vector space. So for all but finitely many K, the dimensions of these cohomology groups grow at least exponentially with G. And let me mention, though this is not really sort of visible from what I've said so far, that we have applications to the unstable cohomology of interesting arithmetic groups. So GLGZ and SLGZ. So these are, as Nishi mentioned, this is a very fundamental group. It's automorphisms of a lattice. And our applications show similar exponential growth for fixed degree below g choose 2 minus g in the cohomology of GLGZ and the cohomology of SLGZ. Sorry, this is a typo. This should say Q. This should say, in fact, Q or, and this is the orientation module. So you imagine the set of positive definite G by G symmetric matrices. This is a real cone, convex, up to scaling. And then GLGZ acts by changing basis, as it would on any quadratic forms. And an element of GLGZ may or may not sort of reverse orientation. Okay, so it is likely that I will not have time to get into how on earth our results are related to the cohomology of GLGZ or SLGZ. But I claim that AG trop is closely related to the symmetric space for GLGZ. And in fact, it has a dense open that is exactly a rational classifying space for GLGZ. So maybe that's what I'll say about that. And there was important tropical input from a previous paper I have on tropical AG. This is joint with Brandt, Bruce, Mello, Moreland, and Wolf. Okay. So let me, so I stated some theorems. One was a structure theorem, a Hopf algebraic structure on cohomology in AG. And the other was a sort of growth theorem that relied on the Hopf algebraic structure and has applications also to unstable cohomology of GL and SL. So I want to give some ideas of proof. I won't be able to give all the ideas, certainly. But let me start with a K-theory of graphs. This is one of the ingredients, and it's one ingredient that I can kind of pick out as almost independent, certainly of independent interest. All right, so let me construct for you a space that is closely related to MG trop, the moduli of tropical curves. But here it is somehow it's not tailored to stable curves. It's a moduli space, a coarse moduli space perhaps, of all graphs, all metric graphs, MGR. And for reasons that may or may not appear in the next few minutes, I claim that this is a reasonable thing to call at least a coarse version of a K-theory space of graphs. Okay, I can't draw it, it's very big. In particular, it has a cube for every single graph. No conditions on the graph. Loops, multiple edges are allowed. The graph could be disconnected. The graph could be empty. That actually is its own component right there. So for example, if your graph is here, you imagine that you have a cube parametrizing all possible edge lengths, A and B, where A and B are real numbers that can go down to 0, or it can go up to infinity. If the number goes to 0, you regard the edge as being contracted. Whereas if the number goes to infinity, you regard the edge as being deleted. In the case of the loop, deletion and contraction look the same, but maybe you can see it in this side. When A goes to 0, this leg or bridge edge is contracted, whereas when A goes to infinity, in the limit, you get the deletion. In this way, you have a moduli space of all graphs, the K-theory space of graphs. This space, it started its life not as a cube complex, but as a simplicial complex. You imagine, okay, so I'm sort of reverse engineering this for you, but let me try to motivate it. You can imagine that you can chop each cube into n factorial triangles, in this case, 2 factorial triangles, that correspond to the ordering of the edge lengths on the graph. And then an ordering, possibly with equality, would give you a sequence of subgraphs in a canonical way. So the way this space is actually constructed is as a geometric realization of a certain simplicial set. The fancy version, which is also important for us, but is not visible on this slide, is a simplicial groupoid, where the P simplices are isomorphism classes of triangular diagrams of graphs. The most important part of the triangular diagram is this sequence at the top, where these feathered arrows denote a literal subgraph, meaning same vertex set, subset of the edges. Let me suppress the data of the rest of the triangular diagram, because up to isomorphism, it can be recovered from the top row. So the cube that we started with, one of the two simplices, one of the two triangles from the cube that we started with is corresponding to this diagram, which roughly you should think of as like you had two vertices and then you have an ordering on the edges depending on which came first in this inclusion of subgraphs. So this is how the K-theory space of graphs is constructed. For me, this is an interesting sort of all genus / loop order at once moduli space of metric graphs. It can be filtered, moreover, like if you're interested in filtering by first Betti number, you can do so. So you have a filtered space now, and famously to some people, you have a naturally associated spectral sequence. Without using those words, I can certainly just talk about the totality of the homology groups of the pairs. So this is FP MGR, graphs with Betti number at most P, relative to graphs with first Betti number at most P minus 1. These again form a bigraded vector space formally, and in fact, they're the first page of a spectral sequence associated to this filtered space, and we call this a graph spectral sequence. The theorem is that this, let's just say for now, bigraded vector space admits the structure of a bigraded bi-algebra, almost a Hopf algebra, but not quite, and it's commutative. And this actually has a sort of space level instantiation, very roughly speaking. Sorry, it can be made precise, but for this slide, it is related in a precise way to the Kahn-Kreimer coproduct on graphs, which I know some people might be interested in and more familiar with than I am. This is the coproduct that takes graph and it splits into the sum over all subgraphs of the subgraph tensor, the contraction. And just to relate to the talk from Monday, the primitives of the, I'm sorry to say, the dual of this bigraded vector space with differential can be related precisely to Kontsevich commutative graph complex in a way I won't state precisely. Okay, so this entire presentation was ahistorical in that I started with the graph part, which is, I guess, a contribution of ours, but it was modeled on the much older approaches of Quillen to the K-theory of rings. So by replacing graphs with projective modules over an appropriate ring, for example, here the integers, we recovered the Quillen construction of algebraic K-theory, which is some space that encodes an interesting sequence of groups associated to a ring via the sequence of homotopy groups. That's a first definition. So the K-theory space, or rather something closely related to it, is obtained again as a geometric realization of some simplicial set. Here, the diagrams are triangular diagrams, not of graphs, but of projective modules finitely generated with appropriate conditions. The resulting space, this is much, this is work of Quillen and Waldhausen, is the one-fold delooping of the K-theory space of the integers in this case. And just like our moduli space of graphs, it can be filtered by rank of module. There's a relationship between graphs and finitely generated Z modules. Every graph has associated to it an interesting free Z module, namely its first homology with coefficients in the integers. In this way, we have a map of filtered spaces. I would like to say it's a map from M graph, the moduli of graphs, to our one-fold delooping of the K-theory space of Z. But it's actually, there's a fancier version where I should have taken like the simplicial groupoid on not just isomorphism classes of diagrams of graphs, but actually the actual diagrams with automorphisms included. But in any case, this is a map of filtered spaces. And I claim that on each filtered quotient, so a filtered piece modulo the smaller one, this map can be precisely related to a so-called Torelli map in tropical geometry that associates to a tropical curve, its tropical Jacobian. There's a lot of work that goes on here. there's actually not, this is not literally true as proved in our paper yet, but it is proved via a zigzag of homotopy equivalences. So the part that I am not having time to talk about, but I think is combinatorially very pleasant, is what is this map on a purely combinatorial level? And that I would refer you to my graduate school paper for. So the final input to our theorems on AG is a theorem that is proved purely in algebraic K-theory, and I'm glad for my collaborators to teach me this stuff, that the Quillen spectral sequence, which is exactly by definition the spectral sequence associated to the filtered space BKZ mentioned a couple of slides ago, is a spectral sequence of Hopf algebras. This is a theorem that's sort of, it's not related to AG on the face of it. It's purely an algebraic K-theory theorem, but roughly speaking, we're able to, through the material of the previous slides, relate the Hopf algebraic structure on this spectral sequence with a Hopf algebraic structure on AG. Okay, I'd better stop there. Thank you for your time.
We have questions for Melody.
So does Torelli give you some like precise relationship between the Hopf algebra on AG and the Lie algebra on MG?
Yeah, sorry, I don't think I'll be able to articulate something sufficiently precise, but yes, our source of cohomology in AG, in weight zero, is by pulling back. So I sort of thought that like AG was more fundamental than MG, and in some sense it is, but at the moment, I think the information flow is going from MG to AG via Torelli. So our source of classes is actually coming from the graph complex, as discussed on Monday, and in particular from the Grothendieck-Teichmuller Lie algebra and these wheel classes in graph homology. Yeah, thank you. Yeah.
The construction of MG trop, which works for surfaces with cusp points, is there an analogous construction of an MG trop for surfaces with fixed geodetic boundary or boundaries of some kind?
Yes, I think that there's relevant work by Louis Ainot and Dan Petterson, and probably other authors I'm not remembering at the moment. But it's interesting to study, right? So like surfaces of genus G with maybe like some marked sort of like disk sort of boundary components and some marked points. And they have cool work that relates this to moduli of handle bodies. Yeah.
Can I just ask a big question? So, like, is there anything interesting you can say about like the maps used to define it as a Hopf algebra? Is there any interesting combinatorics involved in that?
Interesting thing to say about the maps, what?
Involved in defining the Hopf algebra, say like antipodal maps or the antipodes or like coproducts? Do they have some kind of interesting structure inside them, or is it just like the fact that you
Yeah, I'd love to know more. So half of the structure we understand, like if you have, roughly speaking, AG is made of polyhedral cones of quadratic forms, and you can block some quadratic forms. That gives one of the two Hopf algebraic structures. The other one we're getting from the Quillen spectral sequence, and at the moment, we don't have a sort of like concrete polyhedral interpretation. So that's, for me, a really interesting question, and I'd like to understand that better. Yeah.
So this path to understand the MG from Siegel Hopf spaces encounters the famous problem of the shock problem.
Yes.
Does it play any role in your story?
Yeah, let's see. I don't know how to answer that. So yeah, AG trop is very complicated. It involves the combinatorics of perfect quadratic forms, and they're just incredibly complicated. But there's a Schottky locus of the tropical Torelli map, and the image is controlled by a priori a simpler subcomplex that involves just the combinatorics of regular matroids. Roughly speaking, the regular matroid corresponding to a graph is that of its co-graphic matroid. And there's work so there's some interest in studying like the combinatorics of the regular matroid complex replacing the graph complex. It seems subtle so far.
Any other questions? If not, let's thank Melody again.